Good afternoon, class. We are looking at exam one review, covering chapter 2. And we're going to look at the first part. Part 1 will cover section 2.1, the tangent and velocity problems, 2.2, the limit of a function, and 2.3, calculating limits using the limit laws. So those are the three sections for now we're going to cover, and then later on we go to the precise definition, continuity, limits at infinity, also known as horizontal asymptote, derivatives and rates of change, the derivative as a function. Now, I want to make sure everybody understands when we take the exam, because something came up, it's important to know, although there is no proctorio or anything like that, you have to take the exam on your own. So before starting the exam, please read the following pledge. That is, when you take the exam, you have this statement: I pledge on my honor that I will neither give nor receive unauthorized assistance during this exam. Unauthorized action include, but are not limited to, the use of notes, text, graphic calculators, search engine, PowerPoints, or any other resource not explicitly allowed. All right, so we're going to start with the limits of a function, finding limits by numerical and graphical method. Here's the definition. Limit of f of x as x approaches a is L. This is read the limit of f of x as x approaches a equals L. That's how you read it. Now let's look at graphical methodology. As you look at all of these three graphs, the concept of a limit as x approaches a means we are getting closer and closer to a from the left and from the right, but not necessarily at a. That's the concept of a limit. So if we are approaching a from the left, that means we are in this branch. If we are approaching it from the right, we are in this branch. And both of them are moving towards this point. As far as the limit is concerned, it's referring to the y coordinate of that point, which is L. And in all three cases, whether you approach a from the left or right, you get to L as far as the y coordinate is concerned. So that means the limit of f of x as x approaches a is L for all three graphs. What's the difference? If you look at this one, P f of a is also L, which in essence, it means the function is continuous at x equals. If you look at this one, notice we have a solid point. So f of a is the y coordinate of a solid point, which is b, but it's not equal to L. Because they are not equal, it makes it discontinuous. In part C, f of a, we don't have a solid point. We don't even know what's f of a. So f of a is undefined. Nevertheless, the limit exists. Of course, it makes it still a discontinuous function at a. So part A, f of a equals L. Part B, f of a equals B, not equal to L. Part C, f of a is not defined, but in each case, regardless of what happens at a, the limit of f of x as x approaches a equals L. That has got to do with understanding graphs. Now, horizontal asymptotes, short HA, they have a specific definition in calculus. So the horizontal asymptote of the curve y equals f of x is y equals L if the limit of f of x as x approaches negative infinity or positive infinity is L. Vertical asymptotes, VA, short for vertical asymptotes, also have a specific definition. The limit of f of x as x approaches a, this one, limit of f of x as x approaches a from the left, that's the meaning of that negative sign. Limit of f of x as a approaches from the right. If any of them is positive or negative infinity, that gives rise to the equation of a vertical asymptote having the equation x equals a. That's the definition. One-sided limits. A function has a limit at a if the limit of f of x as x approaches a from the left is L. The limit of f of x as x approaches a from the right is also L, which means limit of f of x as x approaches a equals L. And definition of a continuity. The limit of f of x as x approaches a equals f of a. That means the functional value and the limit are identical. Let's look at this example, finding limits by numerical and graphical methods. Guess the value of this. So we want to get this started. So we are looking at the limit of x minus 1 over x squared minus 1 as x approaches 1. And we are looking at this function. We want to find the limit. So this is f of x or y. F of x equals x minus 1 over x squared minus 1 is not defined when x equals 1. Does it matter? The answer is no, because you're not looking at the function at x equals 1. In other words, we are not asking what's f of 1. We are asking what's f of x, what's the y coordinate when we get close to 1. That's the idea of a limit. And so, numerical method, let's evaluate this function with so many decimals, or however many they ask you, for values of x that approach 1 but are not equal to 1. So we are going to look at number 1 as we get close to it, not exactly 1. So we are going to look at the table below. The tables below give values of f of x for values of x less than 1 and x larger than 1. So here's x less than 1. Here's f of x, the same function that was discussed. Let's start with something close to 1 but less than 1. For example, 0.5, 0.6, 0.7, 0.8, 0.9. Believe it or not, even 0.9 is not good enough. It's not close as far as the limit. So 0.99, and then keep on adding nines. As you can see, we are getting closer and closer. So you put it into this, you evaluate it, I give you the answer. So as we get closer and closer to 1, we get closer and closer to these numbers. So we want to figure out what's the limit in a moment. Let's look at the right side when x is larger than 1. For example, 1.5, 1.4, 1.3. Notice I'm getting closer and closer to 1, 1.1, 1.01, and even 1.1 is way too far, even 1.01. Put it into a calculator. This is what you get. So because we go down along the first table and the third table, we're getting closer and closer to 1 from both sides. This from the left, this from the right. Let's look at the last row. The last row indicates that this one gives us this number, 0.5, 0, 0, 0, 25, but from the right gives us 0.499975. And I hope you see it really is giving us the limit. The limit is 0.5. And by the way, if you have any doubts, if you add another 9 here, and if you put another 0 in between, you'll see that they become even closer. And that's the concept of a limit. Now, if we were to graph this, y equals x minus 1 over x squared minus 1, it's a curve where the denominator can't be x equals 1, right? At that point, creates a hole. So as we approach 1 from the left, we are in this branch. As we approach 1 from the right, we are in this branch. Both pieces are moving us towards this hole, which has the y coordinate 0.5. So the graph also indicates the same answer. Let's look at algebraic method, analytical method, which is even more important. To do so, we can factor the denominator. A squared minus b squared is a minus b, a plus b. This is x squared minus 1 squared. Therefore, the denominator is x minus 1, x plus 1. We cancel x minus 1. And now If you plug in 1, I hope you see that you get 1/2 or 0.5. In other words, we used numerical method, graphical method, but more importantly, algebraic method. So you're expected to do algebraic method almost always. As far as these two methods, if the question asks you, you follow that. Otherwise, you always go with the algebraic method, and we will look at that as we go through the process. 2.3, calculating limits using the limit laws. Let f of x and g of x be defined for all x over some open interval containing a. Assume that L and M are real numbers such that the limit of f of x as x approaches a is L, and the limit of g of x as x approaches a is M, two different numbers. Let C be a constant, just some number. Then each of the following statements holds. So the first one reads, this is the sum law of four limits. The limit of f of x plus g of x as x approaches a is the limit of f of x as x approaches a plus limit of g of x as x approaches a, which makes it L plus M. So that means the limit of the sum is the sum of the limits. This one is called the difference. In the same manner, the limit of f of x minus g of x over as x approaches a is limit of f of x as x approaches a minus limit of g of x as x approaches a, L minus M. The rest of them follow in the same manner. So what you see here, the limit of the difference is the difference of the limits. Over here, if you have a constant multiple of the function, you can take the constant out. The limit of the product is the product of the limits, L times M. The limit of the quotient is the quotient of the limits, L over M. However, when it comes to a quotient, a fraction, the denominator can never ever be 0, and you want to be careful with that. And of course, the power limit and the root law are the same thing as well. By the way, I want to add one more thing, maybe here. Limit of a number, let's say k. I'm going to use k as a number. Okay. As x approaches a, it's k. In other words, if you have a constant, doesn't matter x approaches what number because it's independent of x. It doesn't matter what it is. Now, direct substitution property. A continuous function at a has the following limit value. Limit of f of x as x approaches a equals f of x. So just plug in. Functions with the direct substitution property are called continuous at a. If it works, that means the function is continuous at the given point. The squeeze theorem. If f of x is less than or equal to g of x, less than or equal to h of x, when x is near a, except possibly at a, and the limit of f of x, this left side, this function, limit of f of x as x approaches a, is the same as the right side, the limit of h of x as x approaches a equals L, then the one in the middle, according to the squeeze theorem, the limit of g of x as x approaches a must be L. This is also known as the sandwich theorem because g of x is between the two functions. Calculating limits using the limit laws. Here's a warm-up example. Use the limit properties to find the limit of x squared minus 3x plus 7 as x approaches. Let's do that. So Ultimately, we're going to plug in, but for now, using the limit laws, we're going to separate this into 3 pieces. The limit of x squared as x approaches 4, plus the limit of negative 3x as x approaches 4, plus the limit of 7 as x approaches 4. This one is the limit of x as x approaches 4 quantity squared. This one, the negative 3 comes out. Now, according to the limit laws, you have to go this far, and now you can replace these by 4. So you get 4 squared minus 3 times 4. This is a constant, and that I've mentioned that x approaching any number makes no difference. It's 7. And so 16 minus 12 plus 7 is 11. And of course, simply you can plug in. If you plug in right here, you get 4 squared, which is 16, minus 3 times 4, which is 12, plus 7 equals 11. And when it works out, that's fine. Here's example 2. We want to find the limit of, we really want to find the limit of f of x as x approaches 2. Because we want that, we're going to look at one-sided limits. Limit of f of x as x approaches 2 from the left, limit of f of x as x approaches 2 from the right. And you recall, if the limit of f of x as x approaches a from the left and right are the same, the limit of f of x as x approaches a exists and is equal to L. So we are interested in that. We're going to look at it from the point of view of one-sided limit. So we are going to look at, here's number 2, from the left side of 2 along the x-axis. That means we are in this branch, and it's moving us towards this point. Remember, as far as the limit, we never get there. We get to from the left like 1.9999 and so on. So the y coordinate of this point is the limit value, and that is 3. From the right side of number 2, we are in this branch, and it's moving towards this point, and this point has the coordinate, the y coordinate 1. Are these two identical? No. The limit of f of x as x approaches to d and e does not exist. Let's look at f of 2, limit of f of x as x approaches 4, and f of 4. So let's start with f of 2. When we look at number 2, everybody, you look for a solid point. It gives us this point, which has the y coordinate 3. So f of 2 is given, and it has the y coordinate equal to 3. That means f of 2 is 3. What about the limit of f of x as x approaches 4? So from the left side of 4, we are moving this way. From the right side of 4, we are moving this way. And in both cases, we are approaching this hole, which has the y coordinate 4. The limit from the left and right are identical, so the limit of f of x as x approaches 4 does exist, and it's equal to 4. What about f of 4? If you look at number 4, we don't have any solid points. It's not given to us. It's missing in action, undefined. If you said does not exist, it's okay, but it's undefined. That would be the terminology for that. Now, this example is about the concept of vertical asymptotes, reminding everybody vertical asymptote is the following. If we take a limit of a function f of x, as x approaches either a or a from the left or a from the right, and we end up with positive or negative infinity, then x equals a must be the equation of a vertical asymptote. So with that in mind, let's see what happens with the first one. As x approaches 2, so look at number 2. Left or right of 2 makes no difference. In both cases, the answer is going down to negative infinity. For 5, from the left, from the right, both sides is going to positive infinity. Now pay attention to this. I want to make sure we understand what happens. Limit of r of x as x approaches negative 3 from the left. The left of negative 3 like from negative 4, negative 3.5, negative 3.1, negative 3.001. Clearly, the answer is negative infinity. However, from the right of negative 3, positive infinity. And so now we have the equation of a vertical asymptote. All of those are vertical asymptotes. X equals 2 from here, x equals 5 from here, x equals negative 3 from here. This one gives you the same answer, x equals negative 3. And so those are the vertical asymptotes. How do we find limits? To find the limit, just plug in. We're going to look at algebraic method and observe. When we do that, what happens? Well, we end up with a number as we did with the warm-up example, and that was a number, and you're done. So the limit of f of x as x approaches a is a number, or the limit of f of x as x approaches a becomes 0 over some number. It's important to know 0 over some number means 0 over a number other than 0. That is 0, and you're done. Limit of f of x as x approaches a, if it's some number over 0, any number over 0 in the past we said it's undefined, but it really approaches infinity or negative infinity, and we will figure out later on how to find that easily. However, in calculus, most of the time we end up with the indeterminate form. There are different types of indeterminate forms, such as limit of f of x as x approaches a is 0 over 0, infinity over infinity, infinity minus infinity. And what that means is you have to use your algebraic technique to come up with the correct answer. So in short, what it means more work. So if it's 0 over 0, if it's infinity over infinity, if it's infinity minus infinity. So for example, the limit of the square root of x plus 4 minus 2 over x as x approaches you. We plug in. So if I put 0 here, I get 4. Square root of that is 2. 2 minus 2 is 0. The denominator is 0. So you get 0 over 0, which means indeterminate, which means now I have to do something about it, some sort of an algebraic technique to get to the answer. And because that is the case, I'm going to multiply by the conjugate because it's a square root. Because it's a square root, I'm going to multiply by the conjugate of that. So what is the conjugate of square root of x plus 4 minus 2? It's square root of x plus 4 plus 2, because as you recall, a minus b, the conjugate is a plus b, and their product is a squared minus b squared. So now you can't just multiply by this, you also have to divide by it. Why? because you just can't multiply by any number you feel like it. You can multiply by number 1. As you can see, this fraction, because the top and the bottom are identical, it's equal to 1. So you can do that. Now, when you have 0 over 0, it's the 0 in the denominator, which is a problem, everybody. So the 0 in the denominator is the problem. Therefore, you never ever multiply the x by the parentheses. So what do? You keep it as a product, x, parentheses around that. Now the top is a minus b. Let me erase the work. So you're looking at a minus b times a plus b, which is a squared minus b squared. So the numerator is, this one comes out, x plus 4 minus 4. The denominator, notice I didn't do anything. I keep it as a product. 4 and negative 4 cancel each other. X and x cancel each other. Now if I put the 0, I get square root of 4, which is 2 plus 2 is 4. So 1 over 4 is the final answer. So 0 over 0 is indeterminate and it can go anywhere. It can go to 0, it can go to infinity, it can go to some other number. In this case, the technique was multiplication by the conjugate. Now, I want to look at these two questions together, and you'll see in a moment why. If you look at the top one, the limit of x plus 2 over x plus 3 as x approaches minus 3 from the right, and the bottom one, limit of x plus 2 over x plus 3, the same function, but this time as x approaches negative 3 from the left. So what I want you to pay attention is this. Every number, positive or negative, both sides have the same sign. So for example, 2, the left side and the right side. For example, 1.9 here, 2.1 here. Both of them are positive. But if you look at negative 2, for example, on the left side is negative 2.1, on the right side is negative 1.9. Both of them are negative. Fine. The only number that the left and right are different, 0, the left side is negative, the right side is positive. Now, if you don't pay attention to negative 3 from the right or from the left, just plug in negative 3. The numerator becomes negative 1, the bottom becomes 0, and the same thing for the second. But you have to pay attention, and I'll tell you why. For the numerator, it doesn't make any difference. Here's the reason. If I put negative 3 from the right or from the left, when I add it to 2, it becomes very close to negative 1. So whether it's negative 1.0001 or negative 0.9999 makes no difference. So in this case, it's really negative 0.9999 because negative 3 from the right means like negative 2.9. On the other hand, this one means negative 1.0001. It doesn't matter. But since the denominator is 0, it does make a difference. Here's the reason. You are dividing a negative number. You have to know the sign because the denominator is 0. You're going to end up with infinity. But is it negative or positive infinity? You need to know. How do we figure it out? I'm going to show you a simple technique. In this case, negative 3 from the right is like -2. You can even go with -2 because we want the sign, but let's go with -2.9. Now, over here, +3, that gives you 0.1, which is positive. However, here, -3 from the left, like -3.1. So that one gives you positive, okay? This one, -3.1 plus 3 gives you -0.1. Again, I'm interested in the sign here, okay, class? So you can even here use -2 plus 3 is +1 because I just want the sign. Over here, you can use -4 plus 3 is -1. I want the sign. The sign is what? -1 over 0 from the left. This negative infinity, and this is positive infinity. So the technique you use, you actually pick a number to figure out what the sign will be. Very straightforward, very simple, everybody. Find the following limit if you plug in 4 and evaluate it, you get 0 over 0. So when that happens, when you have a rational expression, the technique is factoring. So factor. Now, of course, it's easy to factor those. In this case, x comes out. In this case, you want two numbers. The product is -4, the sum is -3. What I want to mention, if x is approaching 4, and that creates a 0 in the denominator, that x approaching 4 means you should have a factor of x minus 4. X approaching 7, that means you should have a factor of x minus 7. X approaching -4, that means you have to have a factor of x plus 4. And so you do the factoring. So you do have a factor of x minus 4 because, as I mentioned, you're hoping to get rid of that, and because that is the one that takes you to 0 in the denominator, and it's 0 in the denominator that creates a problem you want to get rid of. And now if you plug in 4, you get 4 over 5 as the final answer. So a quick recap. Rational expression, you're taking a limit, results in 0 over 0. X is approaching a specific number. That will help you figure out the factor you need. On a normal basis, if x approaches 4, you should have a factor of x minus 4. If x approaches 10, you should have a factor of x minus 3. Over here, plug in 0, you get square root of 1 minus 1. That is 0 over 0. And therefore, the technique is the same technique we used last time, which means we are going to multiply by its conjugate. The conjugate of this expression is the same thing. Put a plus sign here. You multiply and divide by it. And you recall, of course, a minus b, a plus b is a squared minus b squared. And we get square root of 1 plus h, quantity squared minus 1 squared. We get 1 plus h minus 1. 1 and -1 cancel each other. H goes away. And now if you plug in, this becomes 1 and 1, 2. So the final answer is 1/2. The limit of square root of x minus 6 plus 3 over x squared minus 7x plus 12 as x approaches 6, the very first thing is to plug in and observe. So if I plug in 6 here, clearly this goes away and the numerator becomes 3. This becomes 36 minus 42 plus 12. So the numerator is 3 again. 6 makes this one go away. 36 minus 42 plus 12 is 6. 3 over 6 is 1/2. In other words, don't jump to a conclusion that you have to multiply by the conjugate. First, plug in and observe. It might give you an answer, and you're done. What about this one? Well, plug in, you get 1/3 minus 1/3, 3 minus 3, you get 0 over 0, and therefore it's an indeterminate form. What you have here is a complex fraction. The technique is LCD. From the top and the bottom, you have only two fractions at top. Even if you have fractions at the bottom, you figure out the LCD for all of them. This is the fastest way to go from a complex fraction to a simple fraction. So 3 times x is the LCD. Let's multiply everything by 3x, the top as well as the bottom. Again, notice x is approaching 3. This is 0, so x minus 3 is a problem. You never, ever distribute. You keep it as a product of x minus 3 times 3x because you're hoping it will go away. What happens to the numerator? 3x times 1/3 is x. 3x times 1 over x is 3. So you get x minus 3 in the numerator. 1 over 3x, and the limit as x approaches 3, when you plug in, you get 1 over 9, and you're done. The limit of 5 plus h to the power of negative 1 minus 5 to the power of negative 1 over h as h approaches 0. I hope you see. You plug in 0, you get 5 to the power of minus 1 minus 5 to the power of 1 minus 1. That's 0. And this is h is 0. So you get 0 over 0. So what is the technique? When you raise something to the power of negative, you can flip it over and make it the power of positive. So this is 1 over 5 plus h. This is 1 over 5. We go back to this concept. Complex fraction. And of course, this, if you plug in, gives you 0 over 0. The technique, the same technique that we used here, LCD. And LCD would be 5 times 5 plus h here. So you multiply and divide by. That means you multiply everything by 5 times 5 plus h. Again, I can't repeat this enough. H is approaching 0. This is 0. This is the problem in the denominator. You never distribute. So h times 5 plus h. But the numerator, you multiply. When you multiply these two, 5 plus h goes away. You get 1 times 5 minus, when you multiply these two, 5 goes away, minus 1 times 5 plus h. Right? I'm assuming everybody's okay with complex fractions. And so the numerator, notice the denominator. I didn't touch it. I just write h, 5 plus h in the form of a product. The top is 5 minus 5 minus h. These two cancel each other. So the numerator is h. They cancel each other. The numerator is only negative 1. And now if I plug in, I get 5 times 5, 25 in the denominator, resulting in the final answer of negative 1 over 25. Evaluate the following limits if they exist. The limit of f of x plus 5 g of x as x approaches negative 2. We are given a couple of functions in the form of a graph. F is the red function, g is the blue function. And to do that, we are going to go with the limit laws, and we cut them into two pieces. This piece plus 5 times this piece, and we're going to write the limit of f of x as x approaches negative 2 plus 5, the limit of g of x as x approaches negative 2. Which means now we want this one, the limit of f of x as x approaches negative 2, and then that one. So the limit of f of x as x approaches negative 2 So this is let me use a different color actually. This is number -1, this is number -2. So -2 from the left is going this way, from the right is going this way, and so left and right. So again, from the left here, from the right here, both of them are moving towards the same point with the y coordinate of 1. The limit does exist. Remember the one-sided limit. The limit of f of x as x approaches a from the left and right are L. Therefore, the limit of f of x as x approaches a exists and it's equal to L. For g of x, from the left, we are moving this way. From the right, we are moving this way. And again, the limit exists and it's equal to, we are looking at the y coordinate of that. It's equal to -1. See, this is -1, -2, this is 0, this is +1, +2 along the y-axis. So this limit of g of x as x approaches -2, we are looking at the blue one, the left, the right, okay? And that gives us -1. So plug in, you get 1 plus 5 times -1, which is equal to -4, and all is fine. Now, what about this? The limit of f of x times g of x as x approaches 1. Again, we do the same thing here. We use the limit laws to separate them into two pieces. In other words, the limit of product is the product of the limits, and we're going to look at each piece, starting with this one. So limit of f of x as x approaches 1. Let's erase the rest of them, everybody. So approaching 1 from the left, from the right, both sides will give us this one. By the way, of course, the function is also continuous at that point. So whatever the y coordinate of this point is, which is 2. So that's fine. So limit of f of x as x approaches 1 from the left or 1 from the right, they're identical, it's equal to 2. We are done. We are going to look at the limit of g of x as x approaches 1, and that does not exist. Why is that? Take a look. So from the left, we are going this way, which means we are moving towards this point. And this point has the coordinates. This is 0, -1. This has the y coordinate -2. If we are coming from the right side, from the right side of from the right side of 1, we are moving this way. And now this whole has a y coordinate -1. Since they are not equal, g of x doesn't have any limit. So limit of g of x as x approaches 1 does not exist. Limit of f of x as x approaches 1 equals 2, but not this one. Therefore, the product doesn't have a limit. The limit of f of x times g of x as x approaches 1 does not exist. And we're done. I want to quickly show you the second method. You can look at this one as x approaches 1 from the left and 1 from the right. So if you look at 1 from the left, remember this one from the left and right makes no difference, is 2, but this one from the left is -2. So the product of these two numbers, -4. Now, if we look at it from the right, the limit of f of x times g of x as x approaches 1 from the right, again, it makes no difference. This one left and right is 2. but this one right is different than left. So 2 times -1. And again, these two are not equal. That's the second method to look at it. What about f of -2? So if you look at f of -2, so this is -1, this is -2. Here, look for the solid point. The solid point is here, and this point has the y coordinate 2. G of 1. Okay, so G is this blue function. Let me erase things so it makes it easier to see. So G is the blue one. At x equals 1, you look for a solid point. This is the solid point. And the solid point has the y coordinate -2. Now we are interested in finding the limit of f of x over g of x as x approaches 2, and we say it does not exist. Why is that? So as x approaches 2, see what color I want to use. So x approaching 2 this way, okay? So for the top, the numerator f, it's approaching this number, everybody, whatever the y coordinate is, which is close to 1.5. But for the bottom function is approaching this one, and that is 0. Therefore, the denominator approaches 0 while the numerator approaches a non-zero number. Therefore, it does not exist. So it's some number over 0. If 2x is less than or equal to g of x less than or equal to x to the power 4 minus x squared plus 2, for all x, evaluate the limit of g of x as x approaches 1. G of x is sandwiched between the two functions. We use the squeeze theorem. So we take the limit of 2x as x approaches whatever number was here, which is 1. And so 2 times 1 is 2. The right side is this function. We're going to take the limit of this function as x approaches 1. 1 to the power of 4 minus 1 squared plus 2, that is also 2. And according to the squeeze theorem, because the left and the right, those two functions, f of x and h of x, when we take the limit as x approaches a equals l, the one in between gives us the same answer. Therefore, this must give us the same answer. The limit of g of x as x approaches 1 must be 2 by the squeeze theorem. So when you answer that, you can't stop at limit of g of x as x approaches 1 equals 2. You have to mention by the squeeze theorem. Prove that the limit of square root of x brackets 1 plus sine squared 2 pi over x as x approaches 0 from the right is 0. Now, questions like that, when sinusoidal functions are involved, you have to be creative. And the way it works, we go back to the basic trigonometric functions and we remember sine, no matter what the argument is between -1 and 1. So if sine of alpha is between -1 and 1, sine of 2 pi over x is also between -1 and 1. Now we're going to square both sides. And before we do that, I want to make sure everybody understands, regardless of what number you have, okay, the right side, a positive value, you square it. Regardless of what number you have on the left, if it's negative, you can't say, if you square that becomes +1. So you can't say it's between 1 and 1, but rather it's between 0 and 1. So if you have any negative number, think about it. If you have a number between, let's say, -5 and 2. Now, if you square that, this becomes 4. But this one, you can't say 25. You have to say 0, because on the negative side, okay, that is numbers in between that you have to figure. I mean, this is, I thought I put -2. You have -2. Okay, and this was 2. Okay, let's say this is 1 and 2. Okay, so this one you erase it, you get 4. But this one, any number in between is okay, even 0 is okay. And that's the idea that you want to be careful of. So when you square that, again, both numbers are identical. This one, you square it, clearly. This one, if you square it, you get the same number, 1. So this has to go from 0 to 1. So having said that, let me erase my work. We want to make it look like that. So we got sine. Now we got this squared. So we are going to add 1. And we get the bracket. So if I add 1, this becomes 1, this becomes 2. Again, that's being creative. Okay, that's the trick. And the next one is multiply by square root of x. Now, I want you to be careful. When you multiply an inequality by a negative number or you divide by it, it flips over. But you know x is approaching 0 from the right, so therefore square root of x is positive, therefore the sign remains intact. So you're going to multiply everything, all 3 sides by square root of x, and this expression, okay, is identical to this expression. This one is the same expression. So now you use the squeeze theorem. You take a limit of the left side as well as the right side. As x approaches 0 from the right, both of them become 0, obviously, right? Square root of 0 is 0, square root of 0 is 0. And if that is the case, the one in between, the limit of square root of x brackets 1 plus sine squared 2 pi over x as x approaches 0 from the right must also be 0 by the squeeze theorem. Find the limit of 2x plus 12 over absolute value of x plus 6 as x approaches minus 6. And because we are dealing with the absolute value, we have to look at the one-sided limit. So I'm going to remind you of a couple of things. Absolute value of x by definition is x if x is larger than or equal to 0. And it's minus x if x is less than 0, which means absolute value of x plus 6. You can drop the absolute value if x is larger than or equal to -6. On the other hand, you may drop the absolute value, put a negative sign in front if x is less than -6, because this means if x is positive, you can drop the absolute value. If it's negative, you have to write the minus x means the opposite of x. So with that being the case, because this approaches -6 from the left, okay, because we are in this vicinity, x is less than -6 according to this, then you drop the absolute value, you put a negative in front of it, and the numerator, you factor the 2 out, and you get 2 over -1 or simply -2. The limit of -2 as x approaches -6 from the left is -2. Now, same thing, but limit of 2x plus 12 over the absolute value of x plus 6 as x approaches -6. This time from the right, and from the right puts us here. We can just drop the absolute value. And for the numerator, we take the 2 out. And again, x plus 6 cancel out. But this time, it's the limit of number 2 as x approaches -6 from the right. And we get to 2. Because these two numbers are not the same, the limit of 2x plus 12 over absolute value of x plus 6 as x approaches -6 does not exist. These two are not equal. That's the reason, because of the one-sided limit. If the one-sided limits are identical, the limit exists. The second method is to simplify this first, using that into 2 and -2, and now take a limit, and it will result in the same answer. The limit of the function as x approaches -6 does not exist.